Hello, differential equations fans, and welcome to a video covering first-order differential equations, which we'll classify as separable. In this video about separable differential equations, which will actually split into two parts, the first part, this video, will cover classification of differential equation as separable, as well as strategy for solving it. In the second video, we'll cover applications of separable differential equations. So without further ado, a definition of a separable differential equation. A first-order differential equation is separable if the differential equation dx dt can be written as f of x, some pure function of x, times g of t, some pure function of t. So the name comes from sort of two reasons, and the first is because the right-hand side of the differential equation separates into two different functions. Here's an example of a differential equation that is separable. Dx dt equals sine of x times t times e to the t plus 2x. We can see that the exponential can split into e to the t times e to the 2x by properties of exponentials. And we can formally separate the right-hand side into a function of x, sine of x times e to the 2x, times another function of t, which is t times e to the t. Okay, this is an example of a separable differential equation. Of course, not all differential equations are separable. Here's the differential equation we were working with in a different video when we were looking at slope fields. This is an example of a differential equation which is not separable. We saw that how to solve the integrable differential equation in a previous section, and I'll point out that this integrable differential equation is actually just a special case of a separable differential equation. So you can see that it's a separable differential equation where the function f of x is just 1. Okay, we saw that the solution of this differential equation, the integrable differential equation, was given by finding an antiderivative of g, either using a definite or indefinite integral. And that same strategy is going to allow us to find a solution of our separable differential equation as well. So the second reason a differential equation is called separable is because of the solution strategy. So the strategy for solving is by formally separating variables and then integrating both sides with respect to the independent variable, which in this case is t. So we see that we can rewrite this differential equation as 1 over f of x dx dt equals g of t. That's separated. And then integrating both sides with respect to t, we have the integral of 1 over f dx dt is the integral of g dt. Now from calculus 1, we know that the differential dx is equal to dx dt times the differential dt. So that integrating 1 over f times dx dt is actually the same as integrating 1 over f dx. So integrating that gives us the integral of 1 over f with respect to x ought to be the same as the integral of g with respect to t. Okay, I'll mention that this chain rule is sort of a shortcut. Usually what happens is we go straight from this differential equation dx dt equals f of x times g of t to an integral of 1 over f of x dx is equal to an integral of g of t dt. But really behind that shortcut is the chain rule. Okay, I'll make a couple comments here. Typically, separation of variables yields a one-parameter family of implicit solutions. So given that we can do these two antiderivatives, find these two antiderivatives, usually we won't have an explicit formula for x as a function of t. But we will have a relationship between an antiderivative involving f of x and an antiderivative involving g of t that ends up being an implicit solution of the differential equation. Okay, again, our goal though is to find an explicit formula for the unknown function, again in this case x. So typically it requires a little bit of care to find that explicit solution. Okay, here's an example of a separable differential equation. So we'll start by finding a one-parameter family of implicit solutions to this differential equation dx dt equals t divided by x. So we write the differential equation. separate variables formally, integrate both sides with respect to t, and end up with the integral of x dx is equal to the integral of t dt. Now this is a good opportunity for me to point out a misnomer about separable differential equations. It sort of looks like what is happening here is that the dt's are canceling on the left-hand side of the equation involving the integrals. That's not really what happens, right? dx dt isn't actually a fraction. It's just notation for a derivative. But it's okay for us to remember how to separate variables by sort of thinking about the chain rule being that those things cancel. But just to point out, that's not exactly what's happening. Okay, so in any case, the integral of x dx is equal to the integral of t dt. These are two antiderivatives we can find quickly via the power rule, and I'll write 1/2 x squared equals 1/2 t squared plus c bar, so that I can multiply through and find that x squared is equal to t squared plus c. Okay, so again, that is the implicit family of solutions, right? So this is not an explicit formula for x as a function of t, but it is a relationship between x and t that satisfies the differential equation. And it's quick to see that just by substituting that relationship back into the differential equation. Okay, so if we want to find the family member that satisfies x at t equals 2 equals 1, it's pretty quick. We have to have c equal to -3, and if we want to ensure that x is a positive number, when we go to choose a branch of our square root function, we want to choose the positive branch. Okay, we can see that the solution is differentiable on two intervals. It's differentiable for t greater than square root of 3 and for t less than negative square root of 3. Now, our interval of existence is only one of those intervals, and the way that you identify the interval of existence is by choosing the one that contains the initial t value. So, of course, the initial t value in this case is 2, so we choose the interval of existence t greater than the square root of 3. Okay, similarly, if we want to choose x of 2 equal to -1, we can solve quickly for the family member from our implicit family of solutions. Again, it so happens that we get c equal to -3, but in this case, if we want x to be a negative value, we need to choose the negative branch of the square root. This square root function, again, is differentiable for t greater than square root of 3 and for t less than negative square root of 3, and again, we have to choose an interval of existence corresponding to the initial t value, which in this case happens to be t greater than square root of 3 again. Okay, so the interval of existence for this second differential equation, or the second initial value problem, is the same as the first, but we choose the family member different. Just as sort of a challenge problem, if anyone's had a little bit of experience with conic sections, I challenge you to graph in the xt plane what these different solution branches look like, and you can probably even find a solution corresponding to x of -2 equals 1 and x of -2 equals -1. Okay, so we can talk about that in class if you like. Okay, just as we can solve integrable differential equations with definite integrals in the fundamental theorem of calculus, we can solve separable differential equations with definite integrals in the fundamental theorem of calculus. And the strategy is sort of the same as we saw before, riffing off of the idea of formally separating variables, integrating both sides with respect to t, and then using dummy variables. We'll end up having a dummy variable for x as well as a dummy variable for t. So the equation separates via the chain rule, and we can integrate 1 over f of u du. U here is the dummy variable in place of x from x naught to x, and we can integrate g of s ds from t naught to t, and again s is the dummy variable in place of t. And it happens that this will give us, so long as we can actually do the integrals, an implicit family of solutions that satisfies the differential equation and the initial condition. So this will end up being a solution of the corresponding initial value problem. Okay, so as an example of an initial value problem involving a separable differential equation, here our differential equation is dx dt equals 2 square roots of x times e to the minus t over t. So we'll start by formally separating variables to write the left-hand side as 1/2 x to the minus 1/2 dx dt, and the right-hand side as 1 over e to the minus t. 1 over t times e to the minus t. Integrate both sides, and then we'll introduce dummy variables and limits of integration involving the initial condition x of 1 equals 4. So the left-hand side has a dummy variable u, integrated from 4 to x. The right-hand side has a dummy variable s, integrated from 1 to t. Now the antiderivative of the integrand on the left-hand side is pretty quick, so we can integrate up 1/2 u to the minus 1/2 as just u to the 1/2 and evaluate that between x and 4. The right-hand side, it turns out, is an integrand for which there's no elementary antiderivative, sort of similar to that e to the minus s squared that we saw the other day. So it ends up that we'll just leave that alone and leave it as a definite integral of 1 over s e to the minus s ds from 1 to t. Now again, we can see that this is an implicit solution. It's an implicit solution because we don't explicitly have x as a function of t, but it does satisfy the initial condition. It's quick to see that if t is equal to 1 on the right-hand side, that integral vanishes, and we can see that x to the 1/2 is 4 to the 1/2, or x of 1 equals 2. Okay, so it's quick to see that this does satisfy the differential equation as well as the initial value. Okay, in this case, it's also quick to solve for the explicit solution. So here's the explicit solution. Just move the factor of 2 from the square root of 4 to the right-hand side and square both sides. The explicit solution is the quantity 2 plus the integral 1 over s e to the minus s ds from 1 to t, quantity squared. And for what it's worth, here is the slope field, as well as the solution that goes through x of 1 equals 4. Okay, so that is an introduction to separable differential equations. Again, in this part 1 of separable differential equations, we've seen how to classify a differential equation as separable, and we've seen 2 examples of solving differential equations, solving initial value problems, one using an indefinite integral to produce an implicit family of solutions and then choosing the family member correctly, and the second using a definite integral in the fundamental theorem of calculus. Okay, so that's it for part 1. We'll go ahead and stop here and continue on with part 2, which is applications of these separable differential equations.